In this video we're going to be introduced to the derivative of sine and cosine. So the assumption is that you've already been dealing with sine and cosine functions, and also you've done some calculus before, maybe on polynomials. So we've plotted here in the red y equals cos x and y equals sine x. The x-axis is in radians, and we've got sine x here in blue. So let's look at that first, and this is not a proof, okay, but it is a bit of a demonstration to suggest why the derivative of sine x is what it is and why the derivative of cosine x is what it is. And it's important that we know we are working in radians, because this holds for radians, and degrees needs a different process, an adaptation of this. If we look at the blue line and we look at the, if we looked at the limit of as the secant approaches the tangent, and we're looking at the gradient of those lines, and that means we're looking at the derivative. You've got tangents here. You could do this accurately with your graphics calculator, but we'll just do it roughly for a quick demonstration. And hopefully you'll agree with my observations here. If we look at the places that are pretty obvious where the gradient equals 0 on the cosine, you put a tangent there, and because we know that at that point there we've got a maximum for cosine, for sine x I should say, and you know that is pi on 2 radians, and it's about 1.6. You can see there that'll be a maximum, and you know from your previous work, the tangent at that point would have a gradient of 0, and likewise there's another one, but also at the minima too, and there's another one there. I'm just finding them there as I see them. I was wondering what you notice about cosine x at those points. So here we go. If we've got gradient of 0 there, what do you notice is happening with the cosine graph? What about this one here? What do you notice? It's true for all of them, it appears. So when the gradient of this one here, so when we've got the gradient of sine x equals 0 when cosine value, cosine x equals 0. Interesting. What about other things we might notice here? When is sine x at its apparent steepness? Well, it appears, and like I said, this is not a hard proof, but we can see, like, if we look at this bit here, it gets steeper and steeper. Eventually it gets less steep and less steep. Perhaps that is where the graph is steepest on the way up, and likewise on the way down here, that's where it's steepest in a negative sense. If that were the case, we can see that if we look at this point here where it's steepest, we can see that the cosine graph, the red graph, has hit its maximum, and when this one here has hit its apparent steepness down, if we translate that down, we translate its x value down, we got the minimum value, so the highest negative number, the negative number of the greatest magnitude. And you can see that translates all the way along. You can also see behaviors too. We can see behaviors of the gradient. The gradient's positive. Let me choose a color that I haven't used yet. So if we look at the gradient of cos x here, the gradient is positive and increasing. Okay, it's positive all the way through here, but by the time it gets above the x-axis, it's positive and decreasing. And likewise over here, it's negative and decreasing. It's negative but increasing here. If we look at all of the corresponding bits for the cosine then, is the cosine graph positive and increasing in this zone here? Well, yes it is. It's positive once it goes past that zero gradient point, or that zero there, it is then positive and increasing. By the time it gets to here, it's positive, but it's not increasing anymore. And here, it's positive but decreasing. So we can see the behaviors match as well. And that suggests that the derivative of sine x corresponds with cosine x, and it actually does. Now, that's not a firm proof, and I'll explain where. I won't do the proof in this video, but I'll explain where you can go for a proof. The cosine situation is a bit different. Cosine, the red graph, we look at, well, it's got those, we started with those max and min, where the gradient is 0. And that does correspond with sine. The other way around, sine is 0. Oh, is it exactly the same relationship? Is the derivative of cos equal to sine? Let's see. Alright, well, certainly the zeros match. The zero gradients matches the zeros on the sine wave. So what about the behaviors and the gradients? So when this cos graph is got a positive gradient, we would expect the blue sine graph to be above the x-axis. We'd expect it to be positive, but it's not. It's negative. When we've got a downwards gradient on the red graph, we would expect sine to be down here below, also below, but it's not, it's above. If we looked at the behaviors, we'd be able to eventually understand, just like we did with this sine, that it's actually the derivative of cos x with respect to x is sine negative sine x. So that's interesting, isn't it? There is a proof, but the proof's not covered in this video. It's beyond the scope of the course this video is based on, but you can prove it by applying the limit and differentiation by first principles theorem. If you want to know formally, there it is written nice and neatly, and as I said, this has got to be in radian measure. In another video I'll show what happens with degrees. And using this formula here in a proof will explain why it has to be in radian measure, which is beyond the scope of this video. If we had to find the derivative of y equals 4 times cos x, so we would apply this formula here. So dy dx, the derivative with respect to x. Now we've got 4 times the derivative of cos x. Now remember our rules for differentiation. Okay, so you can, the derivative of a function times a product is the derivative times the constant. Okay, so you remember that from your previous work, that's assumed knowledge. Okay, and so that would be just following that, so we would have negative 4 sine x as our answer. This one here, we've got a function of a function, so we've got basically y equals sine of 3x, where we have a composite function scenario here. So we have to use the chain rule. So making a substitution then, I'm assuming you know the chain rule. We've got u can equal 3x, so du dx equals 3, and we can say y is sine of u, and dy du is cos of u. So using the chain rule, dy dx, sorry, I just changed that back, that should have been dy. I said dy du, but I didn't write it, there we go. So that's a dy du on that previous line there. So dy dx is dy du times du dx in differential notation, which you should be familiar with if you're watching the video, and we've calculated each of those. So that's cos of u times 3. We can write the 3 on the front and substitute back in terms of x, because u was 3x there, so 3 cos 3x. In fact, in general, if we have any scenario where we can use the sine of a function, which would be a chain rule situation, or cosine of a function, we can follow this process here. We take the derivative of the inner function times cos of the outer if we're starting with sine, or if we're starting with cos of a function, we take negative, because then cos becomes negative sine, negative times the derivative of the inner function times sine f of x. So that's a general way of remembering it. Okay, if we have a just like that previous example, this is a version of this here is a version of that, and that is a version of that, which you get. It's a simplified version, just like that example there. This one here, by following the same process, you would just have k some constant. So sine kx, the derivative of that is k cos kx, and cos kx, if you take the derivative of that, you get negative k sine kx, where k is a constant, some real number. So you got a choice. You could just apply the chain rule, or you could work according to that formula there. I tend to use the chain rule myself, but it just goes to show if you want to use this formula here. So we could apply it to that one we can see on our screen, cos 5x squared. So if we know that we need to find f dash of x, that's the inner function. So that's the derivative of 5x squared, which would be 10x. And we need to go, the derivative dy dx will then equal negative 10x sine of f of x, which was originally 5x squared, and we have our answer, negative 10x times sine of 5x squared.